Hello everyone. Welcome back. So we're going to continue our discussion on thermochemistry today, and then we may be able to finish our discussion on this week, but we'll see how we do. Okay, so let's begin here. Last time we were just talking about energy changes between a system under constant volume versus under constant temperature, and what information can we get from these temperature differences. So much like pretty much every chemistry conversion, the conversion from products to reactants to products is really a change in a chemical state, and we can really define that as a change in the energy of the arrangement of atoms. So however we arrange the atoms, usually a reaction goes if there's a lower energy arrangement of these atoms and their electrons. Okay, so last time we were talking about this brick heating a system of gas particles. So as we know that energy total is our energy of our system and everything around it. So we could say, okay, our E total is our energy of the gas plus the energy of the surroundings. So as the brick cools down and the gas in the cylinder becomes warmer, the energy of both the system and the surroundings, they're going to be changing dynamically. So we can say, according to the first law of thermodynamics, that there's no change in the total energy of the system and the surroundings or the universe. So we can represent this with the following equation: E total equals E system plus E surroundings equals 0. So this gives us a handy equation to state, okay, our system is 0, right? So our change in energy should not be, it shouldn't be increasing or decreasing. So our energy should still be getting lost to the surroundings, right? Or to the system. So we should have a total value of 0. Okay. So these equations, they're just kind of familiar ourselves with how energy changes. So if anything, what's important is the energy of the system. Is energy going out of the system or is energy going in? All right. So before the brick was brought into contact with the container, the total energy is the sum of the energy of the gas and its surroundings. So we can say, okay, E total, let's talk about E total. What was it before and after our change here? So we can say E total let's subscript here before. Okay, before equals the energy of the gas before we brought it into contact with the brick plus the energy of the surroundings before we there was an energy change. So after the brick gave off heat, exchanged energy with the gas and our container here, so the total energy was still the same, right? Was still the sum of the energy of the gas and the surroundings. So we can say, because nothing changed about our system really, just that heat either left or transferred. Okay, so we can say after the event, the energy of the gas is still going to be represented by the total here. So E total after. Okay. So those equations still stand before and after the energy transfer. So now the total energy can it can be it can now we could write an equation that relates the total energy before and after the process, and we could say delta energy, or the change in the total energy, equals the energy of total after minus energy total before. And we could say, since energy is constant, we're going to say it's 0. So energy is not changing. Okay. Now, in this equation, we can substitute our variables here and rewrite the equation above to get the following. Change in energy equals energy of the gas plus energy of the surroundings after the process minus the energy of the gas plus energy of the surroundings before. Okay, and we can say that equals 0. So this is what our process looks like if we were to represent it mathematically in terms of energy transfer. And now, now we can represent this. We can rearrange it now, right? So we could say, okay, we can rearrange the like terms here, which is the gas. So we could say total energy equals, okay, energy of the gas after our transformation here minus energy of the gas before. Plus the energy. Okay, energy of the surroundings minus the energy of the surroundings before. And we can say this all equals to 0. So we're combining the like terms here. Surroundings and gas. Okay. So, since we have these differences here, we can actually further, we could further simplify this as the change in the total energy. So I know there's a lot of terms here. Equals the change in the energy of the gas before and after the process, and then plus the delta E of the surroundings. So we can represent it simply like this, okay? All right, so we can simplify it like that, and that's our, so that's how we represent the total energy. And this change should equal to 0, right? Okay. So, however, according to the first law, there's no change in the total energy of the system and surroundings, because we know energy is conserved, right? So the change in energy of the surroundings must be equal in magnitude and opposite sign to the change in the energy of the system, right? So in simpler terms, if energy was lost by the surroundings, in this case, energy was lost by the surroundings from the brick, and it was gained by the gas in the system. So we can now rewrite this equation as we can rewrite the equation as delta E gas equals negative delta E surroundings. Okay, so that's how we can represent the change in energy that's happening between our surroundings and the system, the gas. So one thing you want to note is that when our system gains energy, delta energy of the system is positive, so we gained energy. And when it loses energy, so say something's cooling down and giving off energy or heat to the surroundings, delta E will be negative, just like how the surroundings is, in our case, negative. Okay, so let's move on to scenario 2. Okay, so say now so let's say now there's no kind of like latches or stops to hold the piston in place. So as we heat the gas, its pressure is going to push back on the piston and raise it. So this would be an example of constant pressure, because as we're heating the gas, the pressure is going up, but as the pressure goes up, it's going to be reduced as the volume increases. So we're kind of maintaining a constant pressure throughout the system. Okay, so let's imagine a second experiment here, which the process is the same, but the stops are removed, right? Okay, so the piston can now move upwards. In order for the piston to move, some energy will have to be used to lift the weight of the piston. So in this case, not all the energy is being used to heat the gas. Some is being done to do work on the system. Okay, so lift the weight of the piston. So when the piston moves up, due to the increased pressure in the container from the energy coming off from the brick being transferred to the gas, it will be higher in the Earth's gravitational field and thus have increased energy. Okay, so increased energy. So we're going to call this energy change the delta E of the piston. Okay, so now the energy of the piston is changing. So it's no longer just the energy of our gas, it's the energy of the piston as well. All right. So the total change in energy in this case is going to be equal to the change of energy of the system plus the change in energy of the surroundings, right? So in this case, we could write our generic equation as delta E total delta E gas plus delta E surroundings. Okay, so just like our last example, right? However, now this time the system consists of both the gas and the piston because it can now move, and now it's part of what makes up the container, right? So now we have to insert an additional term here. So delta E total equals delta, so this will be our system here, delta E gas plus delta E of the piston plus delta E surroundings. Okay, and so we know that it should equal 0 here. So let's just write that in here. Okay. So what is the energy doing to the piston, right? So the energy of the piston is increased by a distance of mg delta h. So that's going to be the energy required to move the piston to a certain height above its original position. So it's going to have increased potential energy. So m is the mass in this equation, g is the acceleration due to gravity, and then delta h is the height to which the piston has moved. So the raising of a weight, in this case, requires work. So I defined work here. Work is the amount of force required to act on an object over a distance. So, picking up maybe a jug and raising it to a certain elevation, that's going to require work. So work is a force over distance. So it's actually a unit of energy. So because it takes energy to do work, we could write the change in the energy of the piston like so. We could say delta energy of the piston equals mg delta h. And when we're doing work on the system, or when we're doing work when a system's doing work, that means energy is being expended towards or away from the system. So it's going towards the surroundings. So we label this as negative work. So whenever a volume expands, that's always negative work. That's because energy is leaving the system and acting away from it. So you think about it, the gas particles are working against the piston, so it's losing energy to raise the piston, which then in turn, the energy is going to go to the surroundings. So that's why when you see the gases expand and stuff, you always see a temperature increase. Okay, negative W. All right. Now we could say the first law of thermodynamics, we could say delta E of our delta E total equals delta E gas. So now the weight of the piston, we say it's negative work minus W plus delta E surroundings equals 0. Okay? So then we could say the change in energy of the gas is actually equal to negative work. Oh, sorry. No, that's not what I meant to write. In other words, the change in the energy of the gas and the work done minus W is going to be equal to the negative change in the energy from the surroundings. So what this equation is saying is that the energy that's gained by our system is the surrounding is going to lose that energy. So not all that energy is going into the gas to raise the temperature of the gas. So it's not changing the energy of the gas completely. Some of it is now going into this W term here, which is being used to do work on the surroundings, so away from the system. That's why it's negative. So here we could say, here energy is lost by the surroundings, and that appears in the increased temperature of the gas and the increased height of the piston. Okay, so energy is being used to heat the gas, and it's also used to push the height of the piston up. So we could say some of the energy was used to do work on the surroundings. So this will always be a negative work value. So negative work value here. Okay, so always negative work here. And pushing the piston up, and that's why the sign is negative. So now we can represent the total energy of the system as delta E system. So remember we talked about Q? So now Q is going to be heat transferred from the surroundings to our system, and it's going to be the sum of Q plus W. So these two terms are state path functions. They depend on the path taken. If you think about it, if heat traveled from a longer distance to get to your central heating system, right, and to disperse into your house, it's going to depend on the path taken, right? So if you take a longer path, there's a more probability heat's going to be transferred between two different mediums. And so the amount of heat transferred efficiently definitely depends on the path. And if we think about work, the amount of work it takes to do a certain task or maybe move a certain object will be dependent on the path taken, right? The shortest path will require the least amount of energy to do the work, and the longest path will require the most work. Okay. All right, so let's end this video here, and we'll pick up in the next video, and we'll talk about the signs of Q and the signs of W. Okay, so I'll see everyone in the next video.